This video is about the geologic history of Florida. Normally, a good place to start is with the geologic map, which is shown here. Remember, a geologic map shows the distribution of rocks at or near the surface, and in the case of Florida, the rocks are near the surface and rarely on it because the state is covered with a layer of sediment that obscures most of the geology underneath. So the best way to see the geology of Florida is with cross-sections. I'm going to show two cross sections through Florida. One, A prime here goes through the northern part of the state, including the Panhandle, and B prime runs right down the spine of the state. And here's what the cross sections look like. Before we can interpret them, it's important to recognize that they are drawn with enormous vertical exaggeration. That is to say that the vertical scale is greatly expanded versus the horizontal scale. The distance down the spine from B to B prime here is almost 250 miles, or over 1,000,000 feet. The depth shown on the cross section here, right, this distance here, is only about 600 feet. So the vertical scale is stretched almost 20,000 times relative to the horizontal scale. The result of this stretching is that angles are much steeper on the cross section than they are in real life. Here I've removed some, but not all of the vertical exaggeration. You can see why the map makers used vertical exaggeration. If the cross sections were drawn to scale, you wouldn't be able to see anything. If I zoom in on the image, it gets a little blurry because I've lost resolution with all this squeezing and stretching, but you can clearly see that the layers are essentially horizontal. And that's the point you should take from these cross sections, that Florida basically consists of a stack of rock layers that are very nearly horizontal. To be sure, the rocks aren't entirely horizontal. You can see that they're arched upward in the middle of the state and some of the layers taper towards the middle. But remember, the dip angles here are actually very small in real life, just a few degrees at most. And notice too that there are no significant faults or folds, that there are no igneous intrusions or volcanoes. It's the world's simplest geology, a stack of nearly horizontal layers. Geologists call such simple structure layer cake geology. And interpreting layer cake geology is easy because we just need to consider how each of the layers formed, starting with the oldest layers on the bottom and moving up to the newest layers on top. Speaking of the top, this is what the present surface of Florida looks like. To put it simply, it's flat. Even though the vertical scale bar goes up to 150 meters, there are no parts of Florida anywhere near this elevation. The highest point is found in the Panhandle, right up here near the Alabama border at 105 meters. Most of the state is at elevations lower than 25 meters, and much of it is within a few feet of sea level. So all the interesting geologic things in Florida are found underground. It's also important to point out that the state of Florida occupies only part of a much larger continental peninsula of Florida that juts out into the Gulf of Mexico. The western part of this continental peninsula is underwater and is called the West Florida Shelf. That's this area in yellow and orange over here. The total width of the continental peninsula of Florida is almost 400 miles, about twice as wide as the present state. West of the West Florida Shelf, the depths drop off deeply to this area in green out here, which is underlain by oceanic crust in the Gulf of Mexico. As sea level has risen and fallen in the past, the amount of exposed land on the continental peninsula of Florida has changed. During periods of high sea level, shown here in the upper left, almost the entire continental peninsula was submerged, with just a few islands remaining above water. On the other hand, when sea level was low, during ice ages, when water was transferred from the oceans to continental ice sheets, like seen in the upper right here, almost the entire continental peninsula was exposed. At these times, Tampa would have been a boring inland city like Orlando. Today's Florida splits the difference, but you can see that given the low elevation, it doesn't take a lot of sea level change to radically change the location of the coastline. I want to point out one more thing about the cross sections. Notice that they show rocks as deep as about 600 feet. That's not because there are no rocks deeper than that. It's because the geology above 600 feet is the most important for the economic reasons, specifically as a groundwater resource, and thus is known very well. But there are rocks deeper than about 600 feet, and these rocks tell an important part of Florida's geologic story. This simpler cross-section goes across the middle of the state. It goes right through Tampa and shows all the rocks down to about 15 kilometers. Over the continental peninsula of Florida, the Peninsular Arch, there are about 4 to 5 kilometers of sedimentary rocks on top of igneous and metamorphic basement rock. East of the continental peninsula, a much greater thickness of sedimentary rocks has accumulated in the Atlantic Ocean. But still, think about it. 4 to 5 kilometers is a lot of rock, and this rock tells the story of how Florida formed. The story starts 290 million years ago when the great supercontinent of Pangaea formed. There was one continent and one ocean. As you can see, Pangaea was an oddly shaped landmass with a large internal sea and many mountain ranges running through it. The mountain ranges formed when the various continents collided to create the supercontinent. The range running down the western side is the Appalachian Mountains, which formed when Africa converged with North America. At the time, this mountain range resembled today's Himalayas, with many 20,000-foot plus peaks and a high plateau. In 30 million years, Pangaea would begin to split apart, and the Appalachians would begin their long journey of erosion. Although they still exist today, they are just piddly hills compared to what they used to be. Florida doesn't exist yet, but it will appear right about here at the star. And the Appalachians will play an important role in the geologic history of Florida. Here's a teaser. Almost all of the fine white sand that famously lines Florida's beaches was eroded off the Appalachians. So let's run this movie forward and see how Florida formed and what happened to it. This is a slightly different map that does a better job of showing the continental shelves. The areas in very light blue or white. Pangaea hasn't yet broken apart, but it's about to. By 260 million years ago, we can see that South America is beginning to separate from Pangaea, but Africa remains firmly attached. By 170 million years ago, both South America and Africa have detached from Pangaea, though they remain fused together. A narrow sea has formed between North America and the fused continents, and a little peninsula has appeared attached to North America. This peninsula will become the basement rock beneath Florida. This basement rock consists of igneous and metamorphic rock that has been recovered in deep boreholes drilled into present-day Florida. It's the rock colored pink in this cross-section. Interestingly, when geologists study this rock and look for analogous rocks in other parts of North America, they don't find any. In fact, the only similar-looking rocks are found in Africa. So it appears that when Africa separated from North America, it left a little bit of itself behind, the basement rock beneath Florida. Now we need to revisit the process by which Africa separated from North America because it plays a huge role in the geologic story of Florida. Here again is the paleogeographic map from 170 million years ago, and you can see that North America ultimately separated along the dashed red line, which became the coastline of North America. This coastline captures a little bit of Africa, the continental peninsula of Florida. However, about 10 million years earlier, Africa tried to detach along a slightly different break, shown by the dashed black line. This is nearly the same line as the successful one, again shown in red, except where it crosses the Florida peninsula. Initially, Africa tried to take its little tag of Florida with it when it separated, but North America held on too tightly and managed to keep it. So the earlier zone of separation was abandoned and a new one, shown by the dashed red line, was formed. This new one became successful. Remember what happens when a continent is being rifted or pulled apart. The rocks experience tension, which creates a series of normal faults, creating down-dropped valleys and uplifted blocks called horsts. So imagine what happened during the earlier stage of rifting, when Africa was trying to pull away from North America along a boundary north of the Florida Peninsula. The stretching produced a down-drop depression called a rift valley. This is the area shown in mustard color on this map. If we draw a cross-section down the spine of Florida and across this rift valley just after the successful rifting to the south, it looks like this. To the south, we can see the successful detachment of the African plate and the infant Atlantic Ocean being formed. To the north, we can see evidence of the earlier attempt at detachment in the form of the down-dropped rift valley, shown in yellow. Here's a simpler cross-section shown for a high stand of sea level. The main point is that the rift valley has continued to subside along faults and by cooling, producing a depression that is filled with deep water whenever sea level rises. So, at about 170 million years ago, just after Africa and South America had separated from North America, the first sedimentary rocks were deposited onto the eroded basement rocks of Florida. These rocks consisted of sandstones and shales formed from clasts eroded off of the basement rocks. These would form the bottommost layer in the layer cake geology of Florida. But ever since Africa separated from North America, sea level has been rising and falling, and it's at about this time that a huge carbonate factory develops on the Florida platform. I'll talk more about that in the part 2 of this Florida video series, but basically the conditions become favorable for the deposition of huge amounts of limestone. This limestone is deposited in shallow seas, and these are tropical seas because Florida is located near the equator at this time. Deposition of limestone is coincident with subsidence of the platform, which allows nearly 5 kilometers of limestone to be deposited in shallow waters. So, by 150 million years ago, the Atlantic Ocean and Gulf of Mexico are wide seas, sea level is rising and falling, and nearly pure limestones are being deposited on the Florida platform during times of high sea level. At 75 million years ago, sea level is very high, producing a huge inland seaway across North America that separates the eastern and western sides. Florida, once again, remains underwater. And pretty much remains underwater most of the time until just a few million years ago. Here's what the world looked like 50 million years ago, 25 million years ago, and 15 million years ago. So Florida was basically a submerged continental shelf from about 100 million years ago until relatively recently. But remember, the whole while that Florida was under shallow water on the continental shelf, the trough to the north, representing the failed Rift Valley, was full of deep water. This deep water channel goes by various names. Here it's called the Georgia Channel Seaway Complex, and I usually refer to it as the Suwannee Straits, but it's all the same thing. A deep trough of water that separated the elevated Florida shelf to the south from the mainland of North America to the north, and water was able to flow through this channel from the Gulf of Mexico to the Atlantic Ocean. In fact, this map should really be redrawn to emphasize the fact that the Suwannee Straits contain deep water, not shallow water, sort of like this. Hopefully this makes it clearer that the trough isolated the elevated Florida shelf to the south from North America to the north. Here's a cross-section where you can see the separation better between Florida to the south and the continent of North America to the north.